Part 5, Section 2 of the exercises, salty solution and acid-base reaction. Exercise 32, we consider the following mixture in a volume of 1 liter of solution containing 0.1 mole of NH4Cl, 0.05 mole of CH3COONH4. So determine the concentration of all species present. First of all, we have to know the nature of these salts. These salts are strong electrolyte since no Ksp value given, and they will dissociate completely to their ions in solution. So NH4Cl dissociates completely to NH4 plus and Cl minus, and we obtain 0.1 mole, 0.1 mole. CH3COONH4 dissociates also to NH4 plus and CH3COO minus, and the dissociation is complete. So in the solution, we have two types of species. First, the predominant species are NH4 plus, Cl minus, CH3COO minus. The presence of NH4 plus in water indicate the presence of HCO plus and NH3, but these species are not predominant, are present in low amount, since NH4 plus is a weak acid. By the same way, the weak base acetate will release acetic acid and OH minus, and we can say OH minus and HCO plus are present in all solutions from the autoionization of water. So we have two types. We have predominant species and the species present in low quantities. So practically in the solution, we have a weak acid, NH4 plus, and weak base, CH3CO minus, and we have the spectator ion, Cl minus. So necessary we have reaction between the acid and the base, and we have to see if this reaction is limited or advanced. According to pKa scale, the reaction between NH4 plus and CH3CO minus takes place in the anti-gamma direction, so the reaction between them is limited. And we know if we have in a solution a weak acid and a weak base, and if the reaction is limited between the acid and the base, and if the acid and the base have the same initial concentrations, so we can apply the formula directly. pH equal have pKa couple 1 plus pKa couple 2. In this example, we have weak acid plus weak base, and the reaction between them is limited, but the acid and the base do not have the same initial concentration, so this relation could not be applied in this type of exercise. We write the reaction limited, CH3COO minus plus NH4 plus give NH3 plus CH3COH. Kr of the reaction is equal concentration NH3 times CH3COH divided by CH3CO minus NH4 plus at equilibrium. We transform this ratio, we multiply by HCO plus, and Kr is equal to Ka of the couple NH4 plus divided by Ka of the couple acetic acid. So Kr equal 10 minus 4.5. K of this reaction is less than 10 minus 4, so we can say that this reaction is highly limited, or this reaction practically does not proceed. to remember that the objective is to find the concentration of all ions present in the solution. We write the reaction at T equals 0. We have 0.05 mole divided by V total, or 0.05 mole, NH4 plus 0.15 mole, 0, 0, at equilibrium 0.05 minus X, 0.15 minus X, X, X. So to find the concentration of the species in the solution, we have to find X. Since the reaction is very limited, so the value of X is very low, and X can be neglected with respect to 0.05 and 0.015. So the concentration of acetate at equilibrium is practically the same, or the number of mole of acetate at equilibrium is the same, 0.05 mole. That of NH4 plus is 0.15 mole. So we have to find X for acetic acid and ammonia. We find X from the value of Kr equal X times X divided by 0.05 minus X, 0.15 minus X. We transform Kr to the concentration. So we divide by V total equal 1 liter. If X is in mole, so we have to divide it by V total equal 1 liter. We obtain the same ratio. Kr equal X2 divided by 0.5 times 0.15, and X is negligible as we said, so we can calculate X equals 3.162 10 minus 5. Therefore, X is equal to 4.87 10 minus 4. So we found the concentration of acetic acid and ammonia at equilibrium, which is equal X. And by the same way, we found the concentration of acetate and ammonia at equilibrium, where we neglect X. So in the solution, we have practically two couples. We have acetate, acetic acid, we have NH4 plus and NH3. And these two couples behave as separate couples. So the pH is determined by couple 1, or the pH can be determined by couple 2. And if we use couple 1 or couple 2, we have to obtain the same answer. So according to couple 1, pH equal pKa1 plus log NH3 divided by NH4 plus at equilibrium. And according to couple 2, pH equal pKa2 plus log acetate, the base, divided by acetic acid. And pay attention, all these concentrations are at equilibrium. We add these two relations. 2 pH equal pKa1 plus pKa2 plus log NH3 divided by NH4 plus log acetate divided by CH3COH. So plus log CH3CO minus times NH3 divided by CH3COH times NH4 plus. And these concentrations are at equilibrium, and we calculated the concentrations at equilibrium since we found X. So pH equal pKa1 9.25 plus pKa2 4.75 plus log acetate X times NH3 acetate is 0.05 minus X, and NH3 X divided by NH4 plus 0.15 minus X times X, as X is negligible with respect to 0.05 and 0.15, so we put X in its value and we obtain a pH equal 6.51. So we calculated X and the pH of the solution obtained. The species present in the solution, pH equals 6.51, so HCO plus equal 10 minus 6.51. The concentration of OH minus times HCO plus equal Kw, so OH minus equal 10 minus 14 divided by 10 minus 6.51, so it's equal 10 minus 7.48. The concentration of NH4 plus is practically 0.15 since X is negligible. The concentration of acetate is equal 0.05, and the concentration of ammonia equal concentration of acetic acid 4.87 10 minus 4, and Cl minus is a spectator, so the concentration is practically the initial concentration of the salt equal 0.1 molar. Now we mix 0.2 mole of HCPO4 with 0.2 mole of KCN and 0.05 mole of CH3COH. We have to determine the concentration of the species present and the pH. In this case, HCPO4 is a weak triacid, KCN is a salt electrolyte that dissociates to the spectator K plus and Cn minus, which is basic. So KCN is equivalent to Cn minus, a base. And CH3COH is a weak acid. So we have a mixture of acids with a base. To find the reaction taking place, we put the couples on increasing order of pKa, and we determine the species present. So we have Cn minus, acetic acid, and phosphoric acid. According to gamma rule, we have two reactions possible. The first is between Cn minus and HCPO4, and K of this reaction equal 10 to the power 6.8. So this reaction is complete. And the second is between Cn minus and acetic acid. So acetic acid plus Cn minus gives acetate plus HCN, and K of reaction 2 is equal 10 to the power 4.25. So this reaction is quantitative. Two possible reactions in the same reaction system. We have the same stoichiometry of these reactions. So to compare their advancement or the sequence, we compare the value of K. K of reaction 1 is at least 100 times greater than K of reaction 2. So reaction 1 starts, ends, then reaction 2 starts. So we have to begin by the reaction of phosphoric acid with Cn minus. Phosphoric acid with Cn minus is a complete reaction that produces H2PO4 minus and HCN. At T equals 0, we have 0.2 HCPO4 and 0.2 Cn minus 0, 0. This reaction proceeds till the equilibrium T equal infinity. So at equilibrium, all HCPO4 and Cn minus will react, and we have formation of 0.2 H2PO4 minus and 0.2 HCN. So practically, the first reaction produces 0.2 H2PO4 minus and 0.2 HCN. So what is the quantity or the concentrations of HCPO4 and Cn minus remained? When the reaction proceeds in direction 1, so it's complete, then the reaction is very limited in direction 2. So at T equal infinity, the reaction proceeds in the backward, but this reaction, as I said, is very, very limited. So we have 0.2 minus epsilon, 0.2 minus epsilon, and epsilon, and epsilon. Okay? But epsilon is is negligible because the reaction is limited in direction 2. So we can neglect epsilon with respect to 0.2, and we keep this epsilon if we want to calculate H3PO4 and CN minus remained. So the new solution contains mainly H2PO4 minus 0.2 molar, HCN 0.2 molar, and from the beginning we have non-reacted CH3COH, which is equal to 0.05 molar, and we have the spectator ion produced by the dissociation of K of the salt and equal 0.2 molar. Now we have to look for the new reactions between the species present. The reaction between the species is in the anti-gamma direction. We have reaction between HCN and H2PO4 minus, and another reaction between CH3COH and H2PO4 minus. We know when we have several reactions in the direction of gamma, the more advanced is the greater gamma. But in the anti-gamma direction, the more advanced is that with a smaller gamma. So we have to consider only the reaction between acetic acid and H2PO4 minus. We write the reaction H2PO4 minus plus acetic acid give H3PO4 and acetate. K of this reaction is equal to the concentration of the product H3PO4 times CH3CO minus divided by H2PO4 minus times acetic acid. So it's equal to Ka of the coupled acetic acid divided by Ka of the coupled phosphoric acid equal 10 minus 2.55. So we have to consider this reaction to find the pH of the final solution. We write the reaction at T equals 0. We have 0.2 H2PO4 minus 0.05 acetic acid. The reaction proceed till equilibrium. K of the reaction is very low, so this reaction is limited. We have to calculate X at equilibrium. So we have at equilibrium 0.2 minus X, 0.05 minus X, X, and X. K of the reaction equal 10 minus 2.5 is equal to the concentration of the product divided by the reactant at equilibrium. So equal X squared divided by 0.2 minus X, 0.05 minus X. We solve this equation and we find the X equal 4.94 times 10 to the power minus 3 m. So now we have to do the new balance of substances. What are the substances in the final solution? Acetic acid equals 0.05 minus X equals 0.045. HCPO4 minus equal 0.2 minus X equals 0.195. HCPO4 equal acetate equal X. K plus the spectator is always equal 0.2 molar. And HCN is equal 0.2 molar because HCN did not participate to this reaction. So the new balance of species in the solution, we have acetic acid 0.045, acetate 4.94 10 minus 3 molar. So this is couple 1. And we have HCPO4 equal 4.94 10 minus 3 and H2PO4 minus equal 0.195. This is couple 2. And we have the spectator K plus equal 0.2. If we look to the new balance of the species, and we put increasing order of pKa, we will observe that we do not have new reactions different from the previous written in the previous slide. So we reach the equilibrium state, and at this stage, since we don't have other reaction, so we reach the reaction of control, and at this point we can calculate the pH. The two couples, couple 1 and couple 2, participate to the calculation of the pH, but they behave as free in this solution. So we can use couple 1 in order to calculate the pH, or we use couple 2. If we use, for example, couple 1, we apply Henderson formula, pH equal pKa of couple 1 plus log acetate at equilibrium divided by the acetic acid at equilibrium. We put pKa and the concentration in their values. We obtain a pH equals 3.79. And if we use couple 2, we apply also Henderson, pH equal pKa2 plus log base at equilibrium divided by the acid. We put the values and we obtain the same value of pH. Exercise 33. Determine the pH of the solution by mixing 100 ml of ammonia, which is a base, concentration Cb, with 100 ml of nitrous acid, which is acid, of concentration Ca, according to this concentration. So in this problem, we have acid plus base reaction, and we put the pKa scale. On pKa scale, we determine the species present, ammonia and HNO2. So we have reaction according to gamma rule. The initial number of mole of HNO2 is C times V, since V in milliliter, so the answer is in millimole. We have 2 millimole HNO2 and 6 millimole NH3. We write the reaction. HNO2 plus NH3 gives NH4 plus NO2 minus. At T equals 0 initially, 2 millimole, 6 millimole, 0, 0. HNO2 is limiting, so it will disappear completely. So the number of moles of HNO2 at equilibrium is around 0. We have traces of HNO2. And that of ammonia 6 minus 2, we have 4 millimoles and 2 millimoles NH4 plus and 2 millimoles of NO2 minus. And we know from the beginning that the difference of these two couples is greater or equal 10 to the power 6, so this reaction is complete. It's not necessary to calculate K of the reaction if you can see from the pKa scale that the reaction is complete. So in the final solution, we have NO2 minus 2 millimole, NH3 4 millimoles, and NH4 plus 2 millimoles. So we have a new system, and we have to look for the possible reactions. So in new pKa scale, we put the couples and we determine the species present. We have NH3, NH4 plus, and NO2 minus. NO2 minus is a base, NH4 plus is an acid, so we have a reaction. But since this reaction is in anti-gamma direction, so this reaction is limited. So in the solution, we have practically two separate couples, NH4 plus and NH3, and the other couple is HNO2 and O2 minus. So the pH of the solution can be determined by couple 1, or a student can work on couple 2, and you should obtain the same answer. So the student that work on couple 1, pH equal pKa plus log concentration of the base at equilibrium divided by the acid at equilibrium. And the student that work on couple 2, pKa equal pKa prime of couple HNO2 plus log concentration of NO2 minus divided by the concentration of HNO2, and since we have the same volume, so plus log number of mole of NO2, here we have to correct also NO2 minus divided by the number of mole of HNO2. But it's better to work on couple 1 since the quantities of the base and the acid are given. The student that will work on couple 2, we have only NO2 minus. He has to search for the concentration of HNO2. So the student working on couple 2 should do more calculations. It's better to work on couple 1. So pH equal pKa of the couple ammonium-ammonia plus log, we cancel by V log NH3 divided by NH4 plus. And this number of moles are the number of moles at equilibrium. And the number of moles 4 and 2 are the number of moles at the starting. But since we suppose that NH4 plus is a weak acid of weak behavior and NH3 is a weak base of weak behavior, so the number of moles at equilibrium will be equal practically to the initial number of moles. So equal 9.2 plus log 4 divided by 2 equal 9.5. As I said, if the student work on the second couple, he should obtain the same answer. But pay attention to calculate HNO2 at equilibrium. Part B, we change the initial number of moles of nitrous acid and NH3, so we have 2 millimole and 2 millimole. We write the same reaction, 2, 2, 0, 0. We have traces of HNO2, traces of ammonia, and we have practically 2, 2. So in the final solution, we have NH4 plus and NO2 minus. We have acid plus base, but the reaction between them is limited since it's in the direction anti-gamma. So in the final solution, we have NH4 plus and NO2 minus, which is a solution that contains a weak acid and weak base with equal quantities or equal concentrations and no reaction between them, or the reaction is limited between them, so we can apply directly the relation pH equal half pKa couple 1 plus pKa couple 2 equal 9.2 plus 3.2 divided by 2 is equal to 6.2. Exercise 34. What is the pH of a solution obtained by adding 50 ml hydrobromic acid 0.1 HBr is a strong acid to a bicarbonate? So in this problem, we add a strong monoacid to a weak di base. So the initial number of mole of HCO plus is equal 50 ml times 0.1, 5 millimole. That of CO3 minus obtained from the dissociation of the salt equal 20 ml times 0.2 equal 4 millimole. On increasing order of pKa, we determine the species present. We have HCO plus and CO3 minus. So this reaction is complete in the direction of gamma, since delta pKa is greater than 4. So the reaction HCO plus CO3 minus gives HCO3 minus plus H2O. Initially we have 5 millimoles, 4 millimoles, 0, and the reaction proceeds till T equal infinity since it's complete. So practically we have traces of CO3 minus, epsilon is near 0, and we have 1 millimole of HCO plus remained, a formation of 4 millimoles of HCO3 minus. So in the new solution, we have HCO plus 1 millimole and HCO3 minus 4 millimoles. We we have to do a new pKa scale and determination of the species present. We put the couples. We have HCO plus and HCO3 minus. So we have a reaction in the direction of gamma, and delta pKa is greater than 6, so the reaction is complete. If greater than 4, the reaction is quantitative. To note, in the calculation, quantitative or complete is the same. We work at T equal infinity. So we write the reaction. We have 1 HCO plus, 4 HCO3 minus. This reaction will form H2CO3. So at equilibrium, at T equal infinity, HCO plus is limiting, so we have practically 0. And 3 millimole of HCO3 minus remained, and 1 millimole of H2CO3 formed. Also, we have to search for the new solution obtained, what are the new species present, and to look if you have a reaction. In the new solution, we have H2CO3 1 millimole and HCO3 minus 3 millimole. So we have a mixture between the acid and its conjugate base, H2CO3 and HCO3 minus. So we have a mixture of weak acid and its conjugate weak base. The reaction is limited, so the concentration at equilibrium, because we will have exchange between H2CO3 and HCO3 minus in water till the equilibrium. And since we suppose that the reaction is limited, so the initial concentration we start with are equal to the concentrations at equilibrium. So we apply Henderson formula, pH equal pKa of the couple H2CO3 HCO3 minus plus log base at equilibrium divided by the acid at equilibrium, and we suppose that these concentrations are equal to the initial since the exchange between H2CO3 and HCO3 minus is very weak, so equal 6.36 plus number of moles divided by V, number of moles divided by V, we cancel by V, plus log 3 divided by 1 equal 6.84. Exercise 34, what is the pH of the solution obtained by adding a strong acid to water? When we add acid to water, we have dilution. So we have to calculate the new concentration after dilution, C initial, V initial equals C final, V final. So C final equals C initial, which is 0.1 times 50 divided by V final, which is the V total, 50 plus 200. So the concentration of the acid is equal 0.02. This is the concentration of strong acid. So the pH of the solution depends on the condition of the validity. The concentration is greater or equal 3.2 10 minus 7, so we apply directly the relation pH equal PC0 equal minus log HCO plus in the solution equal minus log C0 equal minus log 0.02 equal 1.7. Part C, we add strong acid to another strong acid. So in the reaction system, we have two strong acids. And pay attention that we have the dilution effect. So we have a mixture of two strong acids. The number of moles of HBr is equal to 5 millimole. The number of mole of HClO4 is equal to 5 millimole. HBr will release 5 millimole of HCO plus, and HClO4 will release 5 millimole of HCO plus, since these two acids are strong. So the number of mole total is equal to the number of mole HCO plus provided by HBr plus number of mole HCO plus provided by HClO4 equal 5 plus 5 equal 10. So the concentration of HCO plus in the final solution is equal to the total number of mole of HCO plus divided by V total equal 10 millimole divided by V total, which is 50 plus 100, so 150 ml equals 0.0667 molar. Pay attention, when N is in mole, V in liter, and when N in millimole, you can put V in milliliter. Or you calculate directly the concentration of HCO plus total is equal to the concentration of HCO plus from HBr plus concentration HCO plus from HClO4, and you apply the dilution effect, C initial V initial equals C final V final. So we have two methods. Or you calculate N total, then you divide by V total, or you start from the beginning by calculation of the concentration HCO plus total, taking into consideration the dilution effect. So the concentration of the acid obtained is greater than 3.2 10 minus 7. We apply directly the relation pH equal PC0 equal minus log C0 equal minus log HCO plus in the solution, and the pH equal 1.176. What is the pH of the solution by adding the strong acid to potassium nitrate? Potassium nitrate is a salt, electrolyte, strong electrolyte that will dissociate to K plus and NO3 minus. And K plus and NO3 minus are both spectator. So K plus would not affect the HBr since no reaction with, and the same for NO3 minus, no reaction with HBr. So the effect of potassium nitrate added is the dilution effect. So the concentration of HCO plus total is equal to the initial number of mole of HCO plus, which is 0.1 times 50, divided by V total, which is 50 plus 130. So the concentration of HCO plus in the final solution after dilution equals 0.0278, and the concentration is greater than 3.2 10 minus 7. So we apply pH equal PC0 directly, and the pH equal 1.556. In part E, we add to HBr, which is a strong acid, we add a strong base OH minus. So in this case, we will have a reaction, and the reaction between the strong acid and the strong base is complete. So first we calculate the number of mole of KOH, which is mass divided by the molar mass, and we obtain 17.82 millimole. We write the reaction. We have HCO plus 5 millimole and OH minus 17.825 millimole. So OH minus is in excess, and the number of mole of OH minus in excess is equal 17.825 minus 5. So we have number of mole of OH minus excess equal 12.825. We divided by V total. V total is equal 50 ml, and we suppose that the addition of 1 gram of potassium hydroxide did not change V total. So V total equal 50 ml. We divide by 12.825 millimole by 50, and we obtain the concentration of OH minus. So we apply directly POH equal minus log OH minus in the solution. Then we deduce pH plus POH equal pKW, and pH equal 13.41. Exercise 43. Consider a solution of NH4NO2 and dissolved in water. So the solution, what is the nature of the solution obtained? First of all, NH4NO2 is a strong electrolyte that will dissociate equally to NH4 plus and NO2 minus. NH4 plus and NO2 minus, the reaction between them is very limited. So NH4 plus will react with water and behave as weak acid that release H2O plus, and K of this reaction is equal to Ka. NO2 minus react with water to give OH minus and behave as weak base, and K of this reaction is equal to Kb. Since we start with equal amount of NH4 plus and NO2 minus, so the quantity of H2O plus formed or OH minus formed will be determined by the values of Ka and Kb. If Ka is greater than Kb, that means we have more H2O plus than OH minus and vice versa. Comparing Ka of the couple NH4 plus equal 5.6 10 minus 10 and Kb of NO2 minus equal 2.5 10 minus 11. So Ka is greater than Kb, and therefore the solution obtained will be acidic. Exercise 46. Calculate the pH of the solution by adding 0.25 mole of HClO4, which is a strong acid since no Ka couple given, to 2 liters of solution composed of acetic acid and its conjugate base CH3COOH-. In this type of exercise, we add a strong acid to a weak acid and a base. So we'll have reaction between the strong acid H2O plus and CH3COOH-. CH3COOH- plus H2O plus, that gives CH3COH plus H2O. The initial number of mole of acetate equals 0.8 mole. HCO plus is 0.25 mole. And we have from the beginning, we have acetic acid, 1 mole. So the reaction will proceed till the equilibrium, and the equilibrium is T equal infinity. HCO plus is limiting, so we have 0.8 minus 0.25, we have 0.55 millimole of acetate, and 1 plus 0.25, so 1.25 mole of acetic acid. Between the acetate formed at equilibrium and the acetic acid at equilibrium, we will have a reaction of exchange. Acetic acid plus water gives acetate plus HCO plus, but this reaction is limited. So the concentration of acetate and acetic acid after exchange between them is practically equal to the initial quantities, 0.55 mole for CH3COOH- and 1.25 mole for acetic acid. So in the final solution, we have the acid and its conjugate base. So we apply Henderson formula, pH equal pKa plus log concentration of the base at equilibrium divided by the concentration of the acid at equilibrium. And since we have the same volume V, so plus log N base at equilibrium divided by N acid at equilibrium, and the number of moles at equilibrium are equal to the initial number of moles. So pH equal 4.39, and the answer is A. Exercise 48.1. We add 0.05 mole of base, strong base NaOH, with no volume change, V total is constant, to 1 liter of weak acid. So we will have a reaction between the strong base and the weak acid, and this reaction is complete. HA plus OH minus, that gave A minus plus H2O. At T equals 0, we have 0.1 mole HA and 0.05 mole OH minus. The reaction proceeds till the equilibrium T equal infinity, and OH minus is limiting. So HA is equal 0.1 minus 0.05, and HA remained equal 0.05 mole. A minus formed equals 0.05 mole. So we have a mixture of the weak acid and its conjugate base, and the initial number of moles are equal. Between them, we suppose that the exchange is negligible, so the number of moles at equilibrium are equal to the initial number of moles A minus and HA, and we apply Henderson, pH equal pKa plus log concentration of the base at equilibrium divided by the acid at equilibrium, and A minus is practically equal HA, so pH equal pKa, and the answer is A. This is a buffer solution, and this exercise is a clear example about the preparation of a buffer solution from the weak acid and addition of base in limiting quantities. 48.2, water is added to the final solution obtained in the previous problem. So what is the pH of the final solution? In the previous problem, we obtain a mixture of weak acid HA and its conjugate base A minus with equal number of moles. And we said that the solution is a buffer solution. So by adding water, the solution is diluted. And as we know, that dilution did not affect the buffer solution. So when water is added to this solution, dilution occurs on the acid and also on its conjugate base by the same way, so the pH does not change. And the answer is B.